So, yesterday we looked at function generation using relative poles, both 2 position and 3 position generation, and that kind of concludes our investigation of the graphical techniques. We will come back to some of them when we do coupler curves in more detail, because we did not really focus a lot on path generation. But that is a separate topic that we will deal with a little bit later. Okay. But graphical synthesis for motion generation, extreme positions, dead center positions, function generation and path generation for like specific points. These are the things that we have looked at, and also slider crank synthesis to some extent for 2 position generation. So, what you will notice with all these graphical techniques is that, one, they are very simple. So, they can give you some quick solutions. They are also very intuitive. So, they give you a very good picture of how to go about it, because it is all based on geometry, which is very convenient. It is easy to understand and easy to apply as well. So, in many cases a graphical solution may be suitable for your application. One of the things that we saw with these methods is, in all of them, what we essentially did was, once you do the synthesis, what you can guarantee is that the linkage can be assembled in those specific positions that you designed for. That is the only guarantee you have. You really do not know what is going to happen in between the positions, and in many cases it may happen that your design may not be suitable because of something that happens in between the precision points that you chose, the specific positions that you chose for your synthesis. So, usually, apart from, if it is a crank, if you want a crank rocker, you do the Grashof check. But apart from that, for other linkages that you design, it is always a good idea to either make a model, either on the computer or a physical model, and see whether it is able to traverse all those positions smoothly. Okay, whether it is able to go from one position to the other. One of the problems that can occur is what is called a change of branch or assembly configuration. A 4 bar can be assembled in 2 configurations, right. You have if you have 4 links, okay, for the same input angle, I can assemble it like that, or I can assemble it like this. Okay. So, if I say this is OA, A, B, this will be A, B dash, OB. So, these are the 2 possibilities, and usually once you assemble it in one configuration, it will only move in that configuration. It will not be able to switch from one configuration to the other without you physically disassembling the linkage and reconnecting it in the second configuration. The cases where it might happen is if you have a neutral, Grashof neutral linkage, not necessarily a parallelogram, but a parallelogram linkage is a Grashof neutral linkage. So, if you have the condition S plus L equal to P plus Q, then when it goes through a change point, it might actually change configurations. Okay. But in general, you will not be able to go from one configuration to the other without physically disassembling the linkage. So, one of the problems that you are likely to encounter is, you may synthesize a linkage, okay, for say 3 positions motion generation, okay, and then you find that you make the model, you try to move it, it is hitting only 2 positions. But you know that the third one also should be on that because it lie, you know, it's the moving pivots lie on circles, right. What may happen is that 2 of those positions may be on one configuration of the linkage and the third position may be on another configuration. So, from the synthesis you could only guarantee that it will be assembled in those 3 positions, but whether it will be able to move. So, in this case it will not be able to move to one of the positions because it lies on the other branch or other assembly configuration of the linkage. So, which is a problem for you. So, one way is to actually make a model and try to find whether it moves to all 3 positions. You can also look at, so the other thing you could do, which is kind of easier to do when you are doing graphical synthesis, is to basically assemble the linkage in the 3 positions. So, say I have designed for motion generation A1 B1, A2 B2, A3 B3, okay, I wanted these 3 positions, okay, and I find easy enough A1, A2, A3 should lie on a circle, so I find OA. Similarly, B1, B2, B3 lie on a circle and I find OB, which is the center of that circle. When I do this, I can assemble the linkage. You can assemble the linkage in those 3, so you can basically draw the linkage in those 3 positions and then look at the angle between the output link and the coupler. So, if you look at this angle, okay. So, you look at the angle between OB, B and A in the 3 positions. So, here also I look at it, the angle is in this direction, okay. Now, in this position if I draw that angle OBB to A, it has changed direction. So, that gives you an indication that it is not going to be able to reach all 3 specified positions in the same branch of the linkage. You would have, so that means it is not a suitable solution for your application. So, with graphical thing you will just have to go back and try something else, maybe change one of the moving pivots, okay. So, that would be, or yeah, so change one of the moving pivots. So, it would be that is one of the disadvantages of the graphical process, because if you keep hitting the wrong solution, then it is going to be quite time consuming. If you get a suitable solution quickly, you are lucky, but if not, it can become quite tedious to look for alternative solutions, okay. So, the way to check is to draw the linkage what we did here was draw the linkage in all 3 design positions. Inspect the angle between a change in direction So, if it is a crank rocker, or a drag link, it means there is a change of branch happening. If it is a Grashof 2, if it is a triple rocker, then it indicates that there is a drive failure, that is there is a toggle position. It means there is probably a toggle position between the two. For a triple rocker, which is a non-Grashof. So, this is a quick way you can determine whether your solution is going to perform as indicated. Again, the other problem could be how it reaches the positions 1, 2 and 3. We have not said anything about taking that into consideration while doing the graphical analysis. So, it may go 1, 3, 2. If it is a crank rocker, you can always start from a different position, change the direction, because it can rotate. So, if I am supposed to reach 1, 2, 3 and instead it is doing 2, 3 or let us say 1, 3, 2. Okay. So, all I have to do is drive it in the, if it is a crank rocker, I just need to drive it in the opposite direction, drive the crank in the opposite direction if it is a crank rocker, right. So, in the crank rocker I can always start at some other position and still manage to get the 1, 2, 3, but that is not the case with a linkage that is not a crank rocker. Okay. I will not have that flexibility to do that, in which case I may again have to go back and redesign. Okay. So, these are some of the problems that we encounter because of the fact that our synthesis is wholly based on specific positions and not on the behavior in between those positions. You will actually find that even with the analytical methods, in many cases we will encounter the same thing, but analytical methods, once you code it, you have more flexibility to cycle through a number of solutions as opposed to the graphical methods. Okay. So, one of the first things we will look at is, so we saw especially for function generation, right, we said, say take the example of the valve opening. You may want the valve to open in a specific relationship with respect to the input. Okay. The input may be uniform, but depending on the application, when I am at the later end of the scale, I may want the valve to open in a certain way, in an earlier end of the scale I may want it. So, there may be a specific relationship. So, I may have, all I am telling you is, okay, I have a black box, I have containing a linkage, I have a specific function x and I want a specific output, and that may happen with this kind of a linkage that is inside this box. Okay. This is what is happening phi and psi. Okay. So, I have a black box which contains a function generator, and I may want a specific relationship between the input and the output in a certain range for the input variable. Okay. If x varies from x0 to xf, in that particular range I want the output to vary in a certain manner. Now if I use a linkage like this, okay, I may be able to achieve that an exact match. So x would be say proportional to phi, okay, the input angle phi, and y is proportional to psi. Okay, I can set it up so that x. Now I can get the exact relationship between x and y, perhaps only at certain specific points of the linkage movement. Those will be the precision points where exactly it matches what I need. Okay. In between I may have error. So if I have, say, if this is x, this is y, and say I am looking for a function that does this. So I have y equal to f of x, which is the desired behavior I am looking for, okay, and this is the desired behavior I am looking for, say from x naught to some xf, okay. Then my actual function generator inside may actually give me something like this. It may match exactly with what I need, at some n precision points. Okay, so there is no error at those precision points, but everywhere else in between I would have some error. So if I look at my this is called structural error. So it is basically based on, that is the characteristic of the linkage that I am using. It is not something that I can rectify by, say, maybe changing the tolerances of manufacturing. Okay. This is how the linkage behaves. The relationship between psi and phi is not going to match exactly the relationship between y and x, and so this is called the structural error of the linkage, and it may be something like, so here my actual, so if I look at these points, what will my error be? My error will be 0 at those points, but everywhere else I would have, there would be a difference between what my actual function is generating versus something like this. Okay, so these at the precision points I have 0 error, but at the ends or in between I do have a non-zero error. Okay, so this orange one is the actual linkage generated function. So structural error is defined as the difference between the generated function which is what the linkage actually produces and the prescribed or specified function for a specified value of the input variable. So, if I look at structural error at say some x equal to some x value, okay, some x dash, then this would be my structural error at that particular point. I would compute what the linkage generates, what I want the actual value of the function to be, the difference between them is the structural error, which I really can't do anything about unless I change the linkage itself. Okay, it is not something that can be rectified by more precise manufacturing or something like that. Okay. So, the desired characteristics are satisfied only at specific points in the range that you are looking at. The range is x0 to xf. So, how do we choose these? Typically, you want to choose the precision points. They may be, if you are looking at a range for the function, if you are only looking at, so for instance in motion generation, if you are only looking at specific positions, then those will be your precision points. Okay, those will be the configurations you choose. In function generation, this is more typical of function generation, where you are looking at the continuous behavior over a range, or in path generation where you would have to look at the continuous behavior there over a specified range. There you want to pick those precision points in such a way that you are minimizing the error over the entire range. Okay. So, you may want the precision points may be a design criterion because you want to hit certain specific spots, in which case you do not really care what happens in between those positions. As long as the linkage is able to move from one precision point to another, that is all you are concerned about. But if you are looking at the behavior over a continuous range, then you are concerned about how the error is going to be in between the points where the error is 0. So, there are different ways to approach it. One is you choose the precision points so that the maximum structural error is as small as possible. And the second approach is you use optimization. The structural error in an overall sense in the entire range. in this kind of an approach, in the second approach, the error may not be 0 anywhere, but the overall error will be minimized. You may get as close to the actual desired function as possible, but the error may not be 0 anywhere. In the precision point approach, you have 0 error at specified points, but the error at other places may be higher. Okay. So, error may not be 0 anywhere. In the case of path generation, your structural error may be defined differently. Function generation, it is easy. You have one algebraic quantity, the angles, so you can just do what we did now. In the case of path generation, you may actually have to define it as a vector between the desired path, you know, so and the displacement vector between where you actually reach versus where you want it to be. Okay. So, it may be that kind of vector, and if it is path generation with prescribed input timing, meaning at a specific point of the input I want to be at a certain path, versus overall path you look at the normal distance how far you are. So, it would differ based on, so those the error computation will be more complex than in the case of function generation, where you can easily see that there is one quantity, there is an input and an output quantity, algebraic quantities that can be related. Motion generation, you may have, because you are looking at both path and orientation there. In the case of motion generation, you have the path of a point plus the orientation of the rigid body. So, you may have to look at multiple structural error curves to analyze the error in those cases. So, let us look at this first approach, which is the choice of precision points. So, this was proposed by Chebyshev, who said that the best linkage approximation to a function occurs when the absolute value of the maximum structural error between precision points and at both ends of the range are equalized. So, this Chebyshev spacing is used to minimize the structural error. So, you choose the precision points in a specific way to minimize the structural error, and then of course you know how to do the synthesis for a specified number of precision points. And this is actually like a first step approach. After that you will start taking smaller intervals and try to minimize the error, but we will only look at this over the range that we are interested in. We will look at the spacing, the precision point spacing. So, it is actually an iterative process that may have to be performed in order to minimize the error. So, you see here that the first precision point is not at the beginning of the range, and the last precision point is also not at the end of the range, okay, because according to Chebyshev's spacing, the errors, there is error at the ends of the range which is equalized with the maximum structural error between the points, okay. So, and for function generation we usually measure the angles from the first. So, you can always take your phi naught equal to 0 without any loss of generality, because in function generation you are only concerned with angular displacements. Once you design the linkage, that relationship is maintained regardless of whether you scale up or down the linkage or reorient the linkage, okay. So, if you take I have my input x in this range and I have my output y equal to f of x. So, j indicates jth precision point. Okay. So, if I look at delta phi, delta x, delta psi and delta y are the desired ranges of the different variables. So, if I look at delta x is mod of xf minus x naught. Typically what we will do is we will assume a linear relationship between x and phi, similarly between y and psi. So, you have phi j minus any phi, actually any phi in the range by x minus x naught will be equal to and you define delta phi by delta x as the scale factor r phi and psi j minus psi naught by yj minus y naught is delta phi by delta y. This is defined as the scale factor r psi. Basically, you can do psi j minus psi 1 by yj minus y1 to determine the value, or y naught or psi naught. It's a linear relationship, so any 2 points that you take, you have the. So r phi and r psi are called the scale factors in degree per unit variable. So there is a geometrical method for the determination of the Chebyshev spacing. So let's say I have a range xf minus x naught, okay, and say I want to determine 4 precision points in this range. So if I determine 4 precision points, I will get 3 angular displacements for this, okay. 4 precision points in this range, okay. So the first thing we do is we draw a circle with diameter equal to the range, proportional to the range, okay, not necessarily equal, it should be proportional to the range. Then if I want 4 precision points, okay, say n is number of precision points, then I have to inscribe an equilateral polygon, a regular polygon equal to 2n sides, okay. So this is an octagon, I want 4 precision points, so I draw an 8-sided polygon, regular polygon, such that 2 of its sides are vertical, okay. Here I have to inscribe it in such a way that 2 of its sides are vertical. So if I look at how would I do that, I know what is the angle subtended by any of these. So if I have (360 by n), in this case would give me 45 degrees, okay. So I would, this would be half of that, so I would draw, and this angle would be 45, okay. So I can determine what would be the side of the polygon by constructing this. I draw this, this would also be 22.5 degrees, okay. So I know the side of the polygon, so I can construct. Typically you only need to construct 1/2 of the polygon, you do not need to construct the full polygon, okay. So I can just construct I know the length, I just construct it like that. Okay. Then my precision points are these. So, from the vertices of the polygon, I drop perpendiculars to the horizontal. So, I have this would be x1, this would be x2, this is x3 and this is x4. So, I can read off, I can measure from this construction the values of x which would form my precision points. And then using a certain scale factor, I would translate it into values of phi, because my x is proportional to phi. Okay. So, if I look at this is obviously x naught plus xf by 2, this point. So, I can write in analytical form, I can write xj as xf plus x naught by 2 minus xf minus x naught by 2 cos of pi by 2n into 2j minus 1. If you want, you can remember this, or the graphical construction is easier, or you can remember it as xj minus x naught equal to xf minus x naught by 2 into 1 minus cos pi by 2n 2j minus 1. So, this is basically delta xj, the distance of a precision point from x naught, okay, delta xj. So, xj equals x naught from the starting point, this distance, x1. So, j would take the values, j will be 1, 2 to n, the precision points. So, I can write xj as x naught plus delta xj. I should, if I say n is the precision points, let me use capital N as the number of, for the polygon, that is equal to 2n. Sorry about that. This is the number of sides of the inscribed polygon. Typically, if you are doing for 3 precision points, because that is what you have learnt synthesis for so far. So, you would have a hexagon, okay, you would have a hexagon, and you can find the 3 precision points of the using the hexagon, okay, and the central point will also be a precision point in that case of the hexagon. So, we will do an example in the next class for function generation using this spacing.